Dear students, we discussed Fourier series of periodic function. Then we discussed even and odd functions and their Fourier series. We have seen that if function is even function, then uh, we can expand it using only cosine terms, and it is called as Fourier cosine series. If function is odd, then we can have Fourier sine series. Now we consider a function which is not periodic. The function f defined on some interval. We extend this function as even periodic function or odd periodic function. Okay, so the expression of that function in the given interval will be copied. Okay, so replicas of that function will be considered. Okay, so such extension uh, is obtained, and then we find Fourier sine series or Fourier cosine series depending on that extension, and this is called as half range Fourier series. So let us see. Half range expansions. Suppose that f is a given function defined on an interval. The half range expansions are Fourier series described below. So first thing, we first extend it to even periodic function. Okay, we extend the function f as even periodic function f1 as shown in following figure. Okay, so it can be better explained using figure. So the first figure is function f. Suppose this is our function f, and the domain is some interval. Without loss, we take domain as interval 0 L. Okay, it may be any other interval. And now let us see how we are expanding this as even periodic function. So in this interval 0 L, we have same expression as f. Okay. This is 0 L, 2L, 3L. Here it is minus L, and so on. So this is same as f, and now we copy this curve in the interval minus L to 0. Okay, so same curve is here. Okay, so both are same. Okay, so in the interval minus L to L, we have even function. Okay, so from 0 to L, we have same function f, and minus L to L, minus L to 0, we consider the same function f. Okay, now we uh, copy this part to everywhere. That means this is function of period 2 pi. Okay, so here we have same function, and here also. Okay, so this will continue, and we call this as f1. F1 is even function of period 2L. Okay, so between minus, whatever is between minus L to L, it is everywhere. Okay, period of f1 is 2L. Okay, so this is first step, and in the second step we find Fourier series of f1. Now f1 is even function, so we find Fourier cosine series. Okay, then we find Fourier cosine series of this even periodic extension f1. F1 is called as even periodic extension of f. Similarly, we can have odd periodic extension. Okay, so let us see the second thing, odd periodic extension. We extend the function f as odd periodic function f2. As shown in following figure. Again, we have our function f in the interval, say 0 to L, and now we extend this to real line. This is 0, L, 2L, 3L, and so on. Okay, so shape of the curve is same in this interval 0, L. And now we take mirror image of this function in the interval minus L to 0. Okay. So here we have mirror image of the part which is in the interval 0, L. Okay. And now we repeat this everywhere. Okay. So we extend in both sides. Okay. This is F2. Okay, this is also periodic function of period 2L. Period of F2 is 2L, and this is even function. So F2 is even function. So sorry, F2 is odd function. So we find Fourier sine series. Then we find Fourier sine series of this odd periodic extension. Odd periodic extension F2. Okay, let us solve one example. Find the two half-range expansions of the function f of x equal to 2k x upon L if 0 less than x less than L by 2 and its value is 2k into L minus x divided by L if L by 2 less than x less than L. Okay, so this is a triangle. Okay, so if we sketch this, then it will look like, okay, so 0 to L, 0, L by 2, L, here when x is 0 it is 0, when x is L by 2 it is k. Okay, and it is straight line. Okay, some constant into x. This is also straight line, but there is minus x. Okay, so slope is different. And when x is L by 2, then this is L minus L by 2, that is again k. Okay, so at L by 2 both the values are k, and when x is L then this is 0. Okay, so this looks like triangle. So rough sketch is like this. Okay, so this height is k. What we have to do, we have to use both the extensions, even periodic as well as odd periodic, as discussed above. So first is even periodic extension. So suppose f1 is even periodic extension of f. We have, so since it is even, we can find Fourier cosine series. Okay, so we have Fourier cosine series for f1 with coefficients given by a0. A0 is equal to 1 upon L integral from 0 to L f1 of x dx. Okay, but we know that in this interval f1 is same as f. Okay, in the interval minus L to plus L, f1 is same as, sorry, in the interval 0 to L, f1 is same as f. So we may write f of x dx. Okay, and now we have two different values. So one is, we can write this integral as from 0 to L by 2 and then plus L by 2 to L. This is equal to 1 upon L into integral 0 to L by 2. Value of function is 2kx by L. 2k by L is constant, x dx, plus integral from L by 2 to L. Second value is 2k L minus x by L. 2k by L into L minus x dx. Okay, now this is simple to find. So this is 1 upon L. 2k by L is constant, so we may write 2k by L square here, and this is integral x, so it is x square by 2 from 0 to L by 2, and here it is L minus x. Okay, so we have L minus x square by 2 into derivative of minus x, that is minus. Okay, L minus x square by 2, limits are L by 2 to L, and this is So upper limit gives L square by 4 divided by 4 means L square by 2 square into 2, that is 8. Lower limit gives 0 minus upper limit, it gives 0. Lower limit x is L by 2, so L minus L by 2, it is L by 2. Okay, but there is minus sign, so this becomes plus. So L square by 4 into 2, that is 8. So this is uh, k, this is 2 into 2, so 4 divided by 8, so k by 2. Okay, L square gets cancelled, so this is a0. Now we find an by definition it is 2 upon L into integral from 0 to L f of x into cos n by x by L dx. So this is 2 by L into integral from 0 to L by 2, and function value is 2kx by L, 2k by L x into cos n by x by L dx plus integral from L by 2 to L, f of x is 2k L minus x by 2k into L minus x by L cos n pi x by L dx. Here n is 1, 2 and so on. Okay. Now we need to use integration by parts. Okay. There is product x multiplied by cosine, and here it is L minus x multiplied by cosine. Okay. So let us see. We call this as 1. We find these integrals separately and then substitute. Okay. The first integral in 1 is, so there is constant we may take outside, so that it is 2k by L is outside, so x into cos n pi x by L. So integral 0 to L by 2 x multiplied by cos n by x by L dx. Okay. So this is first term is x into integral second cos, it is sine n pi x by L divided by n pi by L. So it is same as L divided by n pi. Limits are 0, L by 2 minus integral derivative of x, that is 1. This is integral of second, that is sine n pi x by L divided by n pi by L, means L upon n pi dx. And this is okay, upper limit L by 2. So it is L square by 2n pi sine n pi L, L gets cancelled, so n pi by 2. Then second limit gives 0, because sine 0 is 0. Here also we have 0. Okay. Minus, here we have L upon n pi, integral sine, so it is minus cos. Okay, so I should write here plus cos n pi x by L divided by n pi by L. So it is L square n square pi square. Limits are 0, L by 2. So this is L square upon 2n pi sine n pi by 2, and here upper limit gives, so plus L square upon n square pi square, upper limit is L by 2, so cos n pi by 2 minus lower limit, so cos 0 is 1, so it is minus L square upon n square pi square. Okay, so these are an's. Note that sine n pi by 2. So if n is 1, then it is sine pi by 2, so it is 1. If n is 2, it is sine pi, so it is 0. If n is 3, sine 3 pi by 2 is minus 1. Okay, and so on. So this has different values like uh, 1 0 minus 1 0 1 0 and so on. Okay, similarly cos n pi by 2, if n is 1, cos pi by 2 is 0. If n is 2, cos pi is minus 1. Then 3 pi by 2, cos 3 pi by 2 is 0. Then cos 2 pi, cos 2 pi is 1 and so on. Okay, therefore Fourier cosine series Fourier cosine series or half range expansion is that is half range expansion of f is a0 plus summation an cos n pi x by L. Okay, that is a0, we know a0 is k by 2 plus summation an we just computed, so L square by 2 n pi sine n pi by 2 plus L square by n square pi square into cos n pi by 2 minus 1. So this is an multiplied by sorry, we computed one integral, we need to compute other integral also. Okay, so this is number 2, we need to compute other integral also. Okay, so we don't need this. Now we find integral second term in equation 1, that is second integral. So second thing is we take this 2k by L outside and find integral L minus x cos n pi x by L. The second term is given by integral from L by 2 to L minus x cos n pi x by L. Dx. Okay, again we use integration by parts. Okay, so first term L minus x integral of cos, that is sine n pi x by L. Here it is L by n pi, limits L by 2 to L minus integral derivative of first thing, that is minus 1. So this will be plus into sine n pi x by L multiplied by L upon n pi dx. This is equal to, okay, now we put, if we put upper limit x equal to L, then this will be 0. If we put lower limit, then this is L minus L by 2, that is L by 2. So we have L square upon 2n pi into sine x is L by 2, so sine n pi by 2. Then second term integral sine, it is minus cos, so minus L square upon n square pi square cos n pi x by L. Limits are L by 2 L. So we get this as L square upon 2 n pi sine n pi by 2 minus no limit. So when we put upper limit uh, x equal to L, then we get minus L square by n square pi square cos n pi. Okay. Then this will be plus L square upon n square pi square. Then we put x equal to L by 2, so it is cos n pi by 2. Cos n pi by 2. Okay. Now cos n pi. It is if n is 1, cos pi is minus 1. Okay. If n is 2, cos 2 pi is 1, and so on. So it is minus 1 plus 2. Okay. Note here that uh, when we put lower limit, then we should upper limit gives 0. When we put lower limit, then we should write minus. Okay. So this is number 3. So we substitute 2 and 3 in 1. Okay. So we have an as so from 1 we have an equal to, okay, so this 2k by L we take outside, so that we have 4k upon L square. 4k upon L square, and now integral x into cos n pi x by L, this is by 2. It is L square upon 2n pi sine n pi by 2 plus L square upon n square pi square into cos n pi by 2 minus 1. Okay, so this is first term. Okay, so we have taken L square by n square pi square common, so that it is L square upon n square pi square into cos n pi by 2 minus 1. Okay, what next? Second integral. So plus this integral L minus x into cos n pi x by L. So it is equation 3. Okay, so we write minus L square upon 2n pi sine n pi by 2 minus L square upon n square pi square cos n pi, and plus L square upon n square pi square into cos n pi by 2. Now L square upon 2n pi sin n pi by 2. This gets cancelled. Okay. Now there is L square upon n square pi square cos n pi by 2 twice. Okay. So this is, okay, we can take some terms common. We can cancel L square. So we have 4k. L square gets cancelled. Divided by n square pi square. Multiplied by, okay, this is 2 times cos n pi by 2. And this term minus cos n pi, and this term minus 1. Okay, so minus 1. Okay, so all these are ans. Okay, now we can write Fourier cosine. Okay, so Fourier cosine series of f, that is half range expansion. Okay, so Fourier cosine series of f1, that is half range expansion of f is a0 plus summation an into cos n pi x by L. N is 1 to infinity. Okay, that is a0 is k by 2, and this is plus summation an is written here 4k upon n square pi square into cos n pi by 2 minus cos n pi minus 1 into cos n pi x by L. Okay, so this is the required answer. So this was even periodic extension. Second thing is odd periodic extension. Okay, we extend given function f as odd function, and we find Fourier sine series. Okay, so let f2 be odd periodic extension of f. Okay, so, therefore coefficients in Fourier sine series of f2 are bn, and bn are given by 2 upon L integral from 0 to L f2 of x. Now in this interval 0 to L, f2 is same as f, so we may write f of x into sine n by x by L dx. Okay, now we use similar technique, that means integration by parts as we did in first case, and uh, we find bn to be 8k divided by n square pi square into sine n pi by 2. Okay, so this is homework. You need to check bn is having this form. Okay, n equal to 1 2 and so on. Okay, so therefore half range expansion of f, that is nothing but Fourier sine series of f2. It is given by summation bn sine n by x by L, n from 1 to infinity, and that is summation 8k by n square pi square sine n pi by 2 multiplied by sine n by x by L, n from 1 to infinity. N equal to 1 to infinity. Okay, thank you.